Hey there, welcome back to this video 6-10. We're talking u-substitution, and in this video we're going to go ahead and utilize u-substitution with definite integrals. Just a reminder on the u-substitution process, here it is. In case you missed that first video, you need to identify u and its subsequent derivative. Then we're going to go ahead and substitute these into the original problem. Make sure if you don't have all of the components of the du, you need to go ahead and introduce them. And then lastly, we'll go ahead and integrate. Number 6 is only for indefinite integrals, switching back to x. We're going to go ahead and show you how to integrate and evaluate using the fundamental theorem of calculus without switching back into x. All right, so let's go ahead and kick off looking at a definite integral, and that's our learning intention, to utilize u-substitution with definite integrals. Now, what are the key components of definite integrals? Well, first and foremost, you have the function, what you are actually integrating or taking the antiderivative of, and we call this the integrand. Okay, that's this component. That's f of x, okay? The integrand. Now, what's also important, we've seen here, is the dx, or what you're integrating with respect to, the differential of x, right? That's the infinitesimally small slice of the area under the function, okay? That's essentially our width, okay? And then also, too, what's important, which we haven't really dealt with so far with u-substitution, is the limits of integration. So if you're ever asked, go ahead and write an integral expression to represent this situation or this image, you better bet your bottom dollar, that's a phrase, that you have the limits, you have a function, and then you have what you're integrating with respect to, okay? Now, it's important, all three of these components must be in terms of the same variable. So since we're switching into u's, what do you think we have to also do with our limits? We also have to switch them. Switch the limits of integration also into terms of u, and it's very, very simple and straightforward. I'll go ahead and show you how to do that in this video. AP exam tip: with definite integrals, do not convert back to x. It's just much easier to evaluate the antiderivative in terms of u. Example number 7, here it is. Integrate from 0 to 1. 2x times x squared plus 4 to the power of 3 dx. Now, this integrand here, if it was maybe a power of 2, I might evaluate, or I might consider foiling it out and then just integrating it term by term. But this is pretty complicated. I don't want to do that 3 times. I mean, it wouldn't be impossible, but I don't feel like doing it. It's much easier to say, all right, what if u is equal to x squared plus 4? That would make the derivative of that 2x dx, okay? Now notice, I do have my dx, I do have the 2x, so my du is present. I don't have to introduce anything else. But what I also have to go ahead and account for here is I have to account for my limits. Notice my limits of integration are from 0 to 1, but this is in terms of x. Well, if x equals 0, then what does that make u? So let me go ahead. Well, I have u right here. U is x squared plus 4. Okay, so what's 0 squared plus 4? That is just 4. I'm plugging in 0 into x. And I'm going to do the same thing for our upper limit of integration. X equals 1. 1 squared plus 4, that is 5. U is equal to 5. Okay, so now we're going to go ahead and we're going to do u-substitution. I'm going to switch my limits of integration from 0 to 1 to 4 to 5. And I'm going to replace my u there, the x squared plus 4, that's u to the power of 3. And then 2x dx, that is my du. Okay, so I am integrating u cubed. Well, the antiderivative of u cubed is u to the 4th divided by 4 divided by 4, so I'm going to multiply by 1/4, and I am evaluating from u equals 4 to u equals 5. Now you could just put 4 to 5. I like putting the u equals there, at least in the beginning stages, to make sure, hey, make sure you switched your limits. I guess I should have done it here. U equals, and I guess put this in green. U equals, okay. Now I'm just going to go ahead and evaluate. I'm going to plug this in. So I have 1/4. I'm going to leave that on the outside. And I'm going to plug in these values. We have 5 to the power of 4 minus 4 to the power of 4, which gives us 1/4 times 625 minus 256 is 4 to the 4th, which this is 1/4 of, that gives us 369. And I'm going to take 1/4 of that, which gives us 92.25. Again, if this is a free response question, you can go ahead, you can stop right here. If it's a multiple choice, you may have to go ahead and go further, okay? All right, but that's it. U-substitution with limits of integration, not too bad. Okay. Here's your guys' favorite. Here's a trig example. The integral from pi 6 to pi over 2 of sine of 2x dx. I have a function inside of my function. I have to make sure that I account for that. So u, I'm just going to represent, I'm going to say that that's 2x, and then du will be the derivative of that, 2 times dx. I have my dx, I'm missing the 2. So I'm going to multiply in a 2, and I'm going to balance it with a 1/2. Okay, so there's the 2. What I also have to do now is I have to take my limits, x equals pi 6. Well, if I multiply that by 2, right, because u is 2 times x, so 2 times pi 6, that's going to be pi over 3. And then x equals pi over 2. So I plug that in, plug it in. U, 2 times pi over 2 is just pi. So there's my limits of integration. This is equal to 1/2 of the integral from u equals pi thirds to u equals pi of sine of u du. Okay. All right, we're going to go ahead and integrate. This gives us 1/2. Integral of sine is negative cosine. So I'll add my negative, add cosine of u here. Evaluated from pi thirds to pi. Okay. So this is equal to negative 1/2. I'll leave that on the outside. We have cosine of pi minus cosine of pi thirds. Okay. Cosine of pi, that's easy. That's just the x value on the left side. That's going to be a -1. Minus cosine of pi thirds. I teach my students to use the left-hand trick. So much easier than memorizing all of the trig values. You just have the left quadrant here. So pi thirds, I'm going to put down that angle, and your x value is 1. So your numerator is 1. 1/2. That's cosine of pi thirds. Wizardry. Okay. So this equals 1 minus 1/2. It's going to be negative 1.5, or if I convert this 1, if I change this to a negative 2 over 2, do you guys buy that that is negative 3 over 2 if I combine those? Okay, so a negative times a negative is a positive. 1/2 times 3/2 is 3/4, or 75 cents. There you go. Okay. Example number 9. I had my students do this as a U-try, so you can go ahead and check your knowledge, see if you got this right. You can pause me right now, and I'll show you the answer here in a moment. Okay. The integral from -1 to 2 of x squared e to the power of x cubed minus 1 dx. Hardest part is nailing what u is. Your u should have been the exponent, x cubed minus 1. Now, you know you're doing this right because the derivative of this is 3x squared dx. I account for the dx, I account for that x squared. I am missing the 3, so I'm going to multiply in a 3, which means I have to multiply in a 1/3 in order to balance this. Okay, and you can see there I've accounted for everything. So this integral, 1/3 of this integral is going to be e to the u, which is pretty sweet. Okay, I am needing to go ahead and change my limits of integration, -1 and 2. So I just plug these in. -1 cubed is -1. Take away 1 gives us -2. And then if I plug in 2, this gives us 8 minus 1, 7. So from -2 to 7, those are your limits of integration. Okay, so 1/3 integral of e to the u, good old Spider-Man meme, e to the u, evaluated from -2 to 7. So I go ahead and I plug this in. 1/3 of e to the 7th minus e to the -2nd. And that is numerical, so we can stop there. This one, I don't see much simplification. Maybe if, you know, I mean, I guess you could go ahead and, you know what? I'll show you how you might see this. 1/3 times we have e to the 7th minus 1 over e to the 2nd. And I could see College Board making you make that the same denominator. So 1/3 times, I'm going to say, it'll be e to the 9th over e to the 2nd minus 1 over e to the 2nd. So then this gives us a numerator, if you guys allow me to go a little bit, except this is going to be all over e to the 2nd, and then I have a 3 in the denominator. I could see College Board writing it like that on a multiple choice problem. Okay, I hope I did that right. I think that's right. So, multiple choice, here you go. Example 10, here is a multiple choice question. They say, by using the substitution u is equal to 2 sine of x, which of the following is equivalent to the integral from 0 to pi halves of cosine of x square root of 2 sine of x dx? Well, here's your u. If u is equal to that, then your du is equal to 2 cosine of x dx. And the hardest part for my students on this problem was that their brains were so used to integrating now that they put -2 cosine of x. They were thinking of going backwards. Remember, this is a derivative. When you do your du, it's the derivative. So 2 cosine of x dx. I have the cosine of x. I have the dx. I'm missing a 2, so we have to introduce the 1/2. So this is looking like 1/2 the integral of u to the power of 1/2, right? du. Okay, but remember my limits. So 0 to pi over 2, those are in terms of x. If you plug these in, to u, you would get 0 to 2. Your answer is D. D is the answer. B would have been another good distractor. However, the limits aren't changed, and I'm surprised there's not a distractor in here with D, but with a negative in the front, because that's the most common error is I see students making. When you're finding your DU, they have a negative there. All right, that is it for this video. Like, subscribe, u-substitution, not too bad, not too shabby. Identify your u, that's the most difficult part. I'll catch you guys in the next video. See you later.